This video is on potential energy and force. The equation relating a conservative force, the work done by that force, the change in potential energy, and displacement. All right, so the work done by a conservative force, we've said, is equal to the opposite in the change of potential energy. But a conservative force should also equal the integral of that conservative force dotted with each infinitesimal displacement like that. If we differentiate this entire answer with respect to displacement, what we get is something that looks like this. dw dx is equal to the opposite of du dx. And then when we take the derivative of this thing, it just ends up showing F conservative. Those are equivalent to each other. One of them's the integrated form of the other. If we ignore the work part in this part O right here, we see that the conservative force is the negative derivative of the potential energy with respect to position. Thus, on a graph of potential energy versus position, the force at any particular position is the negative slope of the graph. So we'll show you that here in just a bit. On a graph of potential energy versus position, the force is always the negative slope. So let's try this picture here. You can see that we have potential energy versus position, and we want to know at which of these points is the force large and positive. That means we need a negative slope that's pretty big. So where do we have a negative slope that's pretty big? How about letter G right there? F is equal to 0. That means that the slope is equal to 0. So that's going to be B, D, F, and H. F is moderate and negative. If the force is negative, that means the slope must be positive, and we need a moderate value. So how about point I? Because E is pretty steep, so I'm going to say I on that one. Some of this is a little subjective. Points of stable equilibrium. All right, so equilibrium means the force should equal 0. We're going to explain this later in this video. Down here at the bottom of the gully, point D and point H, those are going to be stable points of equilibrium. B and F, we can skip down if we want already. Those are going to be unstable, and we're going to try and show that to you here in a little bit. How about where the force is moderate and positive? So for the force to be positive, the slope has to be negative, and we need a moderate slope. So I'm saying point C on that one. And what about the force being large and negative? That would have to be positions where the slope is positive and quite so. Point A and point E would fit that bill. Let's see what we can get on this screen now. All right, so here's what we're going to do now. We're going to look at those points of equilibrium where the force is 0. We're going to distinguish here between points of stable and unstable equilibrium. Let's take a point of stable equilibrium, which was point D. So let's look at point D right here where I'm pointing on the left side. If we scoot one of those to the right a bit, what happens to the graph's slope? It becomes positive, which means the force is going to be negative. Which way does a negative force act in one dimension? Typically to the right is positive. So that means a negative force will be directed to the left. Now, what does that mean? We've scooted it to the right, and a force has popped into being that pushes it back to the left. This force that pops into being undoes our original scoot. That's a stable equilibrium point. Let's take the counterexample. Let's take D and let's scoot it to the left. If we scoot it to the left, you look at the picture here where I'm pointing with my marker. If we scoot it to the left, the slope becomes negative, which means the force becomes positive. And on a one-dimensional horizontal axis, which way does a positive force act? It acts to the right. So here again, we've scooted it to the left, and a force has come into being to scoot it back to the right. That's a stable equilibrium point. What about one of these unstable points? How about point F here? That's unstable equilibrium. It's like a ball at the top of the hill, which could easily roll down. If we push that a little bit to the right, what happens to the graph's slope? It becomes negative. If the graph's slope becomes negative, that means the force is in the positive direction, which is that way. Uh-oh, look what's happened. We've scooted it a little to the right, and a force has popped into being that keeps it going that way. That is an unstable equilibrium point. Last one. If we take one of these unstable equilibrium points like F, if we scoot it to the left, what happens to the slope there? The slope becomes positive. If the slope becomes positive, that means the force becomes negative. In what direction does a negative force act? This way. One more time. Uh-oh, we've scooted it to the left. A force has popped into being that continues that. That's an unstable equilibrium point. So at stable equilibrium points, we always get a force that undoes our action. And at an unstable equilibrium point, the force that pops into being always adds to it.